Hi, my name is Raghavendra and this is my video explanation for the part 1 of assignment 2 of Data Science Engineering Methods and Tools course. In this part of the assignment, I'll be answering 5 conceptual questions related to probabilistic modeling, variational inference, and generative models like VAEs and GANs. I'll briefly explain each concept, its intuition, and its importance in practice. Let's get started with the question 1. In this question, we are looking at the evidence lower bound or ELBO, which is used in variational inference to approximate an interactable posterior. We start with the log likelihood, log p of x, and use Jensen's inequality to derive a lower bound by introducing a variational distribution, q of z given x. This gives us ELBO equals the expected log likelihood term minus the KL divergence between q of z given x and the prior p of z. The goal is to maximize the ELBO to make our approximate posterior QZ given X close to the true posterior while also ensuring good reconstruction through P of X given Z. In deep generative models like variational autoencoders, this becomes a core training objective and is optimized through gradient-based methods using the reparameterization trick. Now we come to the second question. In this question, we are comparing two multivariate Gaussian distributions, basically two bell-shaped curves in the higher dimensions. One is the approximate distribution we learn from the data, and the other is a prior we assume, often a simple standard normal. The KL divergence tells us how different these two distributions are. It captures differences in both the mean or center of the distributions and the spread or how wide and in what direction they stretch. For Gaussians, there is a known shortcut. We can directly compute this difference using just the means and covariance matrices. That's powerful because it gives us an exact number showing how far our learned distribution is from the ideal one. This is super important in variational autoencoders because it forms a regularization term in the loss, encouraging the learned latent space to stay close to the prior and stay smooth, stable, and generalizable. Next, we come to the third question. In this question, we discuss the role of the KL divergence term in the ELBO objective. The ELBO has two terms, the reconstruction loss and the KL divergence between the approximate posterior Q of Z given X and the prior P of Z. The KL divergence acts as a regularizer. It ensures that the latent distribution Q of Z given X doesn't drift too far from the prior, typically a standard normal distribution. This helps maintain a smooth and well-structured latent space. If we remove the KL term, the model may overfit to the training data and memorize noise, losing the generalization. The latent space becomes uninformative or chaotic. So the KL divergence encourages compactness and consistency in the latent space, balancing expressiveness with structure. This makes the model more robust and able to generate better, diverse samples. Now we come to the fourth question. In this question, we look at mode collapse in GANs, a common training issue. Mode collapse happens when a generator learns to produce limited variety, generating the same or very similar outputs, even though the real data has many modes. Mathematically, this can occur because the generator is trained to fool the discriminator, not to match the full distribution. So it finds a shortcut, generating only a few samples the discriminator finds most believable. To solve this, we can use Wasserstein GANs, also known as WGANs, which provide smoother gradients and better training stability. We can introduce mini batch discrimination, which lets the discriminator detect lack of diversity, or we can use techniques like unrolled GANs that simulate discriminator updates further ahead. These methods help the generator learn the entire distribution, not just a few modes, reducing mode collapse and improving sample diversity. Next, in this question, we explore posterior collapse in variational autoencoders, a situation where the model ignores the latent variables and relies only on the decoder. Mathematically, this happens when the KL divergence terms in the ELBO becomes too strong and forces the approximate posterior Q of Z to match the prior P of Z too closely, often just becoming a standard normal. As a result, the latent code carries no useful information. The decoder then learns to reconstruct directly from the input, making the variational autoencoder behave more like a plain autoencoder. To prevent this, we can use KL annealing, where we slowly increase the weight of the KL term during training, allowing the encoder to first learn meaningful representations. Another solution is to learn beta varial autoencoders or skip connections, which encourage better balance between reconstruction and regularization. These methods help preserve an informative latent space while maintaining generalization. Thank you very much for watching this video. I hope all the concepts were clearly explained.